In this video, we describe how the digital representation of sound is stored and look at terms such as sample resolution and sampling rate. We also take a look at what is meant by Nyquist theorem. So, what actually affects the quality of a digital converted sound wave? Well, it's a combination of the sampling rate and the sampling resolution. In very, very simple terms, you can think of the sampling rate as being the speed of which the original analogue signal was recorded, and the resolution being the level of detail to which that analogue signal was recorded. Let's have a look. So let's start with sampling rate. As said, this is how often, or sometimes referred to more commonly as the frequency, that you record the amplitude of a sound wave. The more often you record a sample, the smoother the playback will sound. Now we measure this as the number of samples per second, and we call this the hertz. So here in this very simple example, we can see the continuous analogue signal, and we can see that we are taking samples here, here, and here. This represents 1 second. So during a second of continuous analogue signal, we are sampling the sound at 3 points. So that's 3 samples per second, or 3 hertz. Now, obviously a recording rate of 3 hertz is incredibly low. Just as an example, a typical audio file that you get on a CD or MP3 is recorded at 44,100 hertz. So that's sampling the original analogue signal over 44,000 times in a second. Now there's also implications here, because if I double the sampling rate, so here you can see I'm taking readings and sampling the analogue signal 6 times in a second. The implication obviously is I get a much more detailed digital signal. The sample sounds better, but obviously I'm going to end up storing a lot more information, twice the information that I did here. The other factor which affects the size is the sample resolution. Now this represents how many different gradations of amplitude can be represented in a digital waveform. So you can think of this like the amount of information stored with each sample. We measure this in bits, for example 8 bits, and a typical CD uses 16 bits. If we look at my simple example here, you can see we are only recording one of 4 different amplitudes. So that's a very, very small range. I can only take readings at my sampling rate at either this level, this level, this level, or this level. Because I'm only recording 4 different changes of amplitude for my analogue signal, I only require 2 bits to store each sample, because there's only 4 possible combinations. Of course, again, I'm not going to get a very good sound. Now over here, I've got 16 gradations of amplitude being recorded, and once again you can now see that the digital wave that I end up with is a lot more accurate representation of the original analogue wave, so this is going to sound better. Of course, because every sample now requires storing one of 16 values, I need 4 bits, as 4 bits can hold up to 16 combinations of zeros or ones. Again, to give you an example of the sort of quality that's being used in MP3s and audio on CDs, these are recorded as 16 bits. So that means every time a sample was taken of the analogue waveform, 2 bytes are required. But in those 2 bytes, we can store one of 65,536 different amplitudes. In 1928, Harry Nyquist worked out that if you wanted to produce an accurate recording, you needed to use a sampling rate which is at least double that of the highest frequency in the original signal. This theory was proven correct by Claude Shannon in 1949. Now, the human ear is capable of hearing sound in the ranges of roughly 20 Hz up to around 20,000 Hz, with a few people being able to hear frequencies slightly higher. And this is why modern digital audio samples at a rate of 44,000. It's just over double 20,000, with the idea that we shouldn't be able to detect with the human ear any audible loss in quality.